Picture this. You've just loaded up your online cart. You hit that buy button, and literally within the blink of an eye, your order is confirmed. But right in that exact microscopic fraction of a second, an invisible, super high-stakes war is just been waged behind the scenes. Welcome to The Explainer. Today, we're cracking open the incredibly complex AI fortresses built by tech giants, think Stripe, Amazon, PayPal. We're going to look at exactly how they manage to catch sophisticated cybercriminals without ever slowing down your checkout experience.
And that entire battle I just mentioned, it happens on a razor-thin time limit, 100 milliseconds. That is literally all the time the system has to process your data, run some seriously complex machine learning models, and decide if you're a legitimate customer or a highly adaptive malicious adversary. If they fail to decide in time, massive online payment systems just grind to a halt. It's the ultimate test of speed and intelligence.
So here's our roadmap for The Explainer. First, the 100 millisecond war. Then, the extreme imbalance dilemma. We'll look at a defense in depth, followed by connecting the dots. Then, the cost of being wrong. And finally, staying ahead of adversaries.
Okay, let's dive right into Section 1. The 100 millisecond war, the ultimate AI race. The core goal here is absolutely massive. These systems have to score every single transaction, whether that's a payment, a login, or a new account creation, the exact moment it happens. They've got to block the bad guys while instantly approving legitimate activity. But here's the reality of the battlefield. The system is trying to find less than 1% of fraudulent activity, hidden in a massive, sprawling ocean of perfectly fine everyday transactions. I mean, it is the ultimate needle in a haystack problem, and if your AI is just a little bit off, the consequences are completely disastrous.
Which brings us to Section 2, the extreme imbalance dilemma, a delicate balancing act. Because fraud is this incredibly rare, engineers aren't just trying to build a perfectly accurate mathematical model. No, they're managing a very delicate and honestly a very expensive balancing act. Just look at the two ways the AI can fail. First, you have a false negative. Basically, the AI misses a fraudulent transaction, and the bad actor gets away with it. The cost here is straightforward, direct financial loss. But on the flip side, you have a false positive. This is where the AI wrongly declines a perfectly good customer. And the cost here? It's not just one lost sale. It's the fury of a customer who might literally take their business to a competitor forever. This massive asymmetry is exactly what makes the system so incredibly hard to design.
In fact, taking a look at this insider tip straight from staff-level AI engineers, the crucial point is how they frame the whole problem. As the quote points out, you have to frame it as cost-sensitive decisioning, not accuracy. You really have to weigh the asymmetric cost of fraud loss against the cost of an angry, churned customer. It's not just about what's true or false anymore, it's about dollars, cents, and customer loyalty. To manage this, the system doesn't just give a simple yes or no, it can actually output a challenge, like asking for a two-factor authentication code, just to kind of soften the blow.
All right, let's move to Section 3. A defense in depth, building the fortress. So how do you actually build a system that can make these nuanced, highly stressful decisions in under 100 milliseconds? Well, because adversaries are constantly adopting, a single AI model just isn't going to cut it. You need a multi-layered fortress. Every single digital payment passes through a gauntlet of 4 main steps. First, the risk gateway gathers all the data. Second, a rules engine acts as the first line of defense. Third, the heavy lifting machine learning score kicks in. And finally, a decision policy makes the ultimate call. Let's map this out.
Now, what's really interesting here is how beautifully these pieces wire together in real time. An event comes into that risk gateway, which instantly fetches historical and live data. It immediately hits the rules engine. If it survives that, it heads straight into the ML score, pulling from something called an entity graph, which, actually, scratch that. We'll talk about the graph in just a moment. Finally, the decision policy weighs the risk score against those business costs we just discussed and decides whether to approve, challenge, block, or maybe send it to manual review for an actual human investigator.
Let's drill down into the 3 main defenders making the actual judgment calls here. First up, the rules engine. This is your lightning-fast system for hard blocks. So if an IP is on a known blacklist, block it instantly without wasting any computing power. Next is the ML scorer, typically a gradient-boosted decision tree, which is trained on millions of past transactions to recognize known fraud patterns. And finally, anomaly detection. Since supervised ML only knows about past fraud, this unsupervised layer acts as a safety net. It's looking for anything weird or novel that hasn't been seen before. Basically, they work together as a team to cover each other's blind spots.
And regarding that ML score, this really highlights why a specific algorithm called gradient boosted trees, or GBDT, completely dominates this space. Look, while deep neural networks get all the hype these days, GBDTs are just incredibly fast for tabular data. And even more importantly, they offer explainability. They can generate reason codes. If our customer's transaction is blocked and they complain, well, regulators and customer service teams need to know why. You can't just say, well, the black box said so. You absolutely need an interpretable core.
Moving on to Section 4, Connecting the Dots, High Signal Features.
At the end of the day, an AI is really only as good as the data feeding it. So what is the system actually looking at to spot a thief in milliseconds? One of the absolute highest signal features is called velocity. Imagine a stolen credit card. A fraudster isn't just going to buy one coffee, right? They're going to try to run 10 expensive transactions in 2 minutes before the card gets shut down. Velocity features are essentially like digital stopwatches tracking these rapid bursts of activity. But think about the engineering required here. Tracking this globally for every single user and retrieving it for the ML model in under 100 milliseconds, that is a massive, streaming technical feat.
The second major feature is the entity graph, and this brilliantly illustrates how the AI outsmarts organized crime. Fraudsters will often create dozens of fake accounts, but they might use the same laptop or the same proxy IP address or link the same underlying bank card. An entity graph maps all these hidden connections. So, if a brand new account tries to buy a laptop, but the system sees its device ID is linked to 5 other accounts that previously triggered chargebacks, bam, the system shuts it down instantly.
Let's look at Section 5, the cost of being wrong, evaluating the AI.
So, how do engineers actually measure if this massive, complex fortress is doing its job? Well, if you look at this advice from system design experts, it completely shatters traditional machine learning assumptions. It says, don't report accuracy under less than 1% fraud they're misleading. Think about it for a second. An AI that simply approves 100% of transactions is technically 99% accurate, but it's also completely useless, and the company goes bankrupt. Traditional metrics completely fail here.
Because of that, they use a totally different scorecard. Offline, engineers use metrics like PRAUC to handle that extreme data imbalance. But online, out in the real world, it is all about the bottom line. They look at the fraud loss rate, literally the stolen dollars divided by total volume. And the ultimate metric is the cost-weighted error. This mathematically combines the dollar loss of letting a bad guy through with the estimated business cost of insulting a good customer. Everything is tied directly back to a business cost matrix.
Which brings us to our final section, Section 6, Staying Ahead of Adversaries, the Cold Start Problem.
The hardest part of this entire system isn't just the speed, it's the delayed feedback. When a fraudster steals a card today, the true owner might not even notice and file a chargeback with their bank for maybe 30 to 90 days. This creates a massive blind spot known as the feedback loop flaw. Because if your AI gets a little too aggressive and blocks anything even slightly risky, you never get a chargeback report on those blocks. You never actually find out if you were right or if you just turned away thousands of perfectly good customers. You basically create this self-fulfilling prophecy, and your model stops learning the true state of the world.
So I leave you with this final, somewhat provocative thought. If your AI blocks every risky transaction, how will it ever learn what new fraud looks like? To keep the model honest, engineers actually have to occasionally approve or challenge borderline risky transactions on purpose. They literally have to let a little bit of potential danger into the system just to gather the labels, explore the landscape, and learn what new, evolving fraud patterns look like. It is a continuous, never-ending digital arms race, where perfection is just impossible, but rapid, intelligent adaptation is everything. Thanks for joining me on this explainer. And hey, next time you click Buy Online, take a quick second to appreciate the 100 millisecond war happening right beneath your fingertips.